And last time we talked about the Euler's methods, and it's one method about the solving the. This is the one method about solving the initial initial value problem. And let's see. So this is what we have in the Euler's methods. And at the very first beginning, and then we try to do some Taylor expansions here, and then we just skip the last item. This is the error item, and we got okay. Let's skip the error item, and then we write the equation. And this is the Euler's methods. And there's one question asked by the student after the class, and then the student asked, so what's your solution? What is your solutions to this problem? You get W0, W1, W2, W3, W4, and what's the solution? Is this the final solution? The question is not. So these are all solutions, W0, W1, W2, W3, and W4. And now let me draw the picture here. Okay. Picture is, so for example, let's say the function. So at the end of time, at the end of the day, what is the solution of initial value problem? Y. So the true solution, it should be the true solution should be a function yt, and then the t is on the interval on the interval 0 and 2 in between this, right? And so the question is that from this Euler's method, and what do you get? So let's see. Let's just draw these pictures. For examples, maybe the true solutions, and then it's a continuous curve here. Continuous curve here. Maybe sometimes it's it has more regularity than those, but this is something on the interval 0 to 2. 0 to 2. This is a function yt. And what you calculate, and then that is W0, W1, W2, W3, and 4. And it's just some approximations value. So there are some nodal points here, 0, 0.5, and then 4, 1, and 1.5. And then, so here we have the y evaluate at t0, y evaluate at t1, and then y evaluate at the t2, y evaluate at the t3. They are the nodal point, the time nodal point here. This is the t, and then this is the y value. And you will see, and we have so many y values, and then evaluate at the time nodal points. And what is the W? W is just the some approximation value to this. So maybe the W0 is here, and then maybe the W1 is here, W2 is here, W1 is here, and then W3 might be here, and then W4 might be here. So if you take a look at the points here, they are the approximations to this orange point. And then the orange point are on the curves. And then, but the green points are the approximations to the orange points at those nodal points. And this is the solutions to this initial value problem. And that is not just the last one is the not just the last one is the solutions to the equation. And this is the things. And next, I'm going to talk about something. Okay, it seems that we need to also cover the sequence methods. Okay. That's it. And let us just finish this part first, and then I will go back to the sequence methods later. Because I want to tell you the whole story here. And so next, let us talk about, we cover one example. Yes, and then there's the example here. And then we find out that throughout the time, the area is becoming bigger and bigger for the nodal points. And also we see this in the theorem, and then that's why we have a bigger and bigger area throughout the time. And this is because this is the error bound, and then this is the two solutions. Y function, and then you evaluate at the time nodal point Ti. And this is the approximations to the YTI. And so we calculate the difference, and then the theorem tells us that, okay, so if you have such a things here, and then you have the error bound, and then this is the H step size, and then what's the H step size? This is the, so let's see. And let's say you have n nodal points, let's say you have T0, T1, and then to the Tn. T0, T1, and then to the Tn. And then they are equally distributed throughout this interval AB, and then your H step size is the B minus A divided by N. And this is the step size M. What's your M? Your M is the secondary bound. Now, which means that, so look at this, which means that if you have a smaller bound for the secondary, and then this area is becoming smaller. And so, and also we have the step size, and then with the order one here. And here, this part, if you take a look at the Ti, and then the Ti is increasing, and then A is not changing, L is not changing. And then so that's why as the time increase, and then the area is becoming larger and larger. And this is why. And also, as you can see here, the effect of the L, actually, this is the exponential function of the L, and then this is the linear function of L. So you can expect that when the time increase, let's see. So, I mean, actually, you will find that when the L is becoming larger, and then this error bound is becoming bigger. And then which means that if you have a Lipschitz continuous function, and then with a bigger constant L, and then actually you are expecting a bigger error. Does it make sense? So you will see some effect here, and then this is great for the phenomena you must see in your numerical example. And this is how to, so people actually mathematics researcher, especially the numericals methods researchers, they would do this. So first they do run some numerical sample, and then they observe some phenomenon, and they prove the theorem, and then to double check if we have the phenomenon in the numerical example, and then if we can use the theorem to explain the phenomenon we observe. So here we observe that the error is becoming bigger and bigger when the time increase, and that. But here we also have the theorems and then prove here, and then to showing what we observed before. And this is the things. And then let's see. Let's go to the next part. The next part, I'm going to talk about some things about the how to calculate the error bounds. Yes. So here, you got the you got such a theorem here, and then this is the error bound. And so now let us calculate the error bound for these questions. And we are going to make use of this theorem and then calculate the error bound for the one questions. So let's see. This is the example, and you have one questions about this. One or two. I guess just one questions about this on your homework. On your homework 6. So here we have the question and then the IVP problem. It looks like this. This is initial value problem. And then y prime t, that is the first derivative, equals to yt minus t squared plus 1. And this is the same as the first example's equation. 0 to, this is the time interval, and then your initial value point is 0.5. And so here we decide, okay, the step size is 0.2. This is the same as we have in this example 1. Let's see. So here the question is that please use the theorem 5.9 to estimate to find the error band for the approximation error. So let's see. Let's copy everything from the theorems, and then which means that if you are doing some, if you are doing homework, or if you are doing the final exam, and then you can look at your lecture notes and then find out this formula. But your final exam would not be so easy. It could be very difficult. And so now we do some copy and paste, and then this is from the theorem 5.9, and then we got this. And now what you need to figure out, let's see, what need to figure out, we have the things we need to figure out is several things. So the things you need to figure out is, we already get the step size h is 0.2. And then we also have the, we don't know the L number, M and L number, and then this is what we want to figure out. And A is just the 0. This is the right and left endpoint of the interval, and A equals to 0 here. So now what we need to do, first of all, we need to get the band for the second derivative, because M is the, this is the M, and the M is the upper bound for the second derivative. So now the question is that, okay, and this is the equation, and then how can you get the second derivative from this equation? You don't know the exact solution. So when the exact solution for one IVP problem is more difficult than to calculate the second derivative here. So what should we do? Actually, let us see. There's some magic here. We can do it. So the magic is that, okay, you don't know. So this is a question we don't know. The exact solution, YT. And how can we calculate the, how can we compute the second derivative? And then this is a question, the second derivative. And this is the questions we have here. And then, so you will see, actually, we don't need to know the exact solutions YT, and we can calculate it in this way. So what's your function again? Your IVP problem might look like this. It's y prime t and then equals to fty, right? And from this, you are going to take the derivative on the both sides. Let's take the derivative. Take derivative about the time t on both sides, and you will get this. And on the left-hand side, actually, you already get first derivative, and then you take the derivative again, and then that is your second derivative of the yt. And on the right-hand side, you are going to get the derivative of this and dt. And now you should be very careful here. Your variable t, the variable of the function f, you have two variables. And one is the t variable, and then another one is the y variable. And something you need to be very careful is that the y is also a t function. So what you need to do is to first to get the derivative. So I need to point it out. The y is also a t function. So if when you do the derivative about the t, the time t, and then which means that you need to get the derivative about the t variable. And also, you also need to get the derivative about the y and times the fty, tyt. But this is kind of complicated here, but let's see one concrete examples we have. And the concrete examples we have is the examples we have here. And then if we want to calculate the second derivative, and then which means that we are going to get the derivative for these equations on both sides. Hence, you have y prime t prime t, and then equals to the derivative of the yt, and then minus the t squared plus 1, and then dt. And as you can see here, we got, let's see, we actually have this one, the yt, it should be the first one. This is just y prime t, and the second one is just the -2, and this is the derivative. And now, what should we do to calculate the? Let me see, the y prime t again, and then it's equals to the yt, and then minus the t squared, and then plus 1, and then -2. And this is the function. I think I missed something here. The bound for this function. Suggestion is what? Yes, so y prime t equals to the yt and the minus t squared plus 1.
I mean, the one above that. Yeah. Maybe 2t instead of 2.
You said this is y prime and then
Y prime t minus 2t.
Oh, 2t, yeah, 2t. So there's something here I am not sure about. So let's see. The next things, wow, this is very interesting. This one, it doesn't give us, so the textbooks is going for like doing with the exact solution, but it is not doing in this way. But we need to estimate this double prime t, and then with the informations we get from the questions. And so we take the first derivative, and then we have the y prime t, and then minus 2t. And now what we get, it should be the, so we also need to estimate the bound. And then let's see the L first. The L, it should be the Lipschitz constant, and then we actually can Lipschitz constant of the f function, and then we are going to get the it's in terms of the variable y. And so we got the variable y, and then it should be equals to 1. And so hence the L constant, and then could be 1. And here it says this one, it should be something, so looks like this. I cannot believe it. So this one, it should be, this is a very good question. Actually, we can compute the derivative in this way. We don't have the error bound here. So let me think of this later on. So what we need to bound is also bound this yt function. But here we cannot have any information from the yt. We can bound it, but I'm not sure how to bound it from here. So, but I'm going to copy down their textbook value of the bound for this one first, and then later on come back. Let's come back to this on Monday. And at the very first beginning, I think this is just an easy calculation from the equation. But now we have something here. So the textbook here, and then it says, okay, the y prime tt is bounded by a number, and then that is the 0.5 e squared, and then minus 2. And then for the time t, and that is in between the 0 and 2. And the textbook is using the exact solution, and then this is just picks me off. And then it should not be using that exact solution. We don't know the exact solution at the very beginning. So this is the second derivative bomb, and then we come back to this. And then the problem here, as you can see, and then actually we need to bound the yt here. And we got to the solution if we can bound this one. So let's see if we have the m and l, and then this is our m number, and then this is our l number, and then we have the bound for the error, and then it's just the, let's copy them here, and we just need to substitute every numbers we know here. We have the 0.2, and then that is the step size. For the m number, and then we just do some copy and paste, and then that is the 0 square e squared, and then minus 2, and our L is 1. And here we have the 1 here for the L, and then A should be just 0. So that's the things, and then it's the TI, ETI on the right hand side. And this is the bound. And which means that if we want to get the bound for the, so for the initial point, and now we have already set up the W0. And then the W0 should be exact, so we don't need to estimate the error for the W0, because the W0, and then we just set it to be the initial value. And for the W1, and that is just the estimation, because our step size is h equals to 0.2, and then so for your time 1, the T1 is just the T1 is just the 0.2, and then minus the W1, and then it equals to, so it's bounded by this. It should be bounded by, so what we need to change here is just changing the number we have. Actually, we can simplify this a little bit, and then divide it by 2, and then this is just equals to 0.1, and then the time 1 here, and then it's 0.2, And as you can see here, all the things becomes number, and then we can calculate it with the computer or calculator. And this is the bound for the first approximations nodal point. And if you calculate in the computer, and then this one is this one, the number. And if we calculate the error bound for the W2, and that is the 0.4, and this is the nodal point T2, and then minus the W2. And actually what we need to change from the equation is just change the time Ti. So we just need to change this one here, the Ti, and then 0.4, and then it becomes 0.4, and then we have the error bound looks like this. And this is how we compute the error bounds. And if you compare the exact solution, the exact error to this error bound, and then you will find out that each time, and then the actual error is bounded by the numbers we calculated here. And I'm not doing all the calculation here. And then at the end, you are actually getting the Y20 and then minus the W10, and then you will get error bound for the number for this last approximations nodal point. And this is how we compute the error bound, and then we have one thing's missing. So I just claim that we don't need to know the exact solutions to bound that to get the bound. Yes, actually we should have some things to do here. But the textbook is calculating the exact solution, and then the exact solution here is 2t plus 1 squared, and then minus the 0.5 et, and then it calculates the second derivative and then bound it. And then, but this is not the things I believe we need to do here. We need to do the derivative calculation, and then calculate the derivative here, and then use some information we know from the equation, and then to bound what we have here. But let's see, and now I'll come up with a method to estimate the right-hand side next time. And so this is the things, and then let's see. This is just the Euler's method, and then you will see that we use the Taylor expansion here, and then we use two items on the right hand side, and then skip the last every item here. And as I mentioned, we can also do Taylor expansion and then use more items here, and then in the Taylor expansions. So that's the higher order Taylor's expansion, Taylor's fault methods. And this is the next part. And so the higher order Taylor's method, and this is quite similar to what we have here, but we keep more items from the higher order Taylor's methods. And actually we have the same problem, and then that is the IVP problem. And we have the derivative equals to FT and then YT. And the time is between the A and B, and your initial values is alpha. So this is the problem setting, and now we are doing the same things as the Euler's methods. It's the Taylor expansions, but we keep more items in the Taylor expansions. And so now let's say you already divide the intervals AB into let's say into n equals subinterval, equal length subinterval. And which means that your step size here is h divided h equals to b minus a divided by n, and your nodal points are T0, T1, and then T2, and then all the way to the Tn. This is your nodal points. And now let's do the Taylor expansions around Taylor expansions. Once again, we are doing the Taylor expansion. Taylor expansion at the point ti plus 1, and then around the point ti. And so if we do the Taylor expansion here, and then we get the yti plus 1, and then the equals to the yti, and plus, so this is the first derivative item, and then times the ti plus 1 minus ti, and this is just the h. So I'm going to replace this one with h, and plus the y prime, it should be second derivative ti, and then 2 factorial, and then h squared, and then plus the y third derivative ti, and then 3 factorial, and then h3. And let's see, and all the way to hn, and then n factorial, and then y n here. This is the n derivative here, ti, and we have the error item n plus 1, and then n plus 1 here, factorial, when n plus 1, and then this is the ci. And as you can see here, we use n plus 1 derivative, so maybe we should add one assumptions to the y. There's exact solutions y, so we assume that the yt is in this n plus 1's continuous space of the interval AB, on the interval AB. So this is also the assumption, and with that, under that assumption, then we can do this Taylor expansion, and the ci here is in between ti plus 1. So let's go back to take a look at the Euler's methods. In the Euler's methods, and then we do the same, something similar, and then but this is the Taylor expansion first item, and then but now we have n items here, and this is the error item, and then we just drop it, and then we get the something is the this is the equation here below here. So let's see, we are going to drop the error item here. This is the error item, and then we are going to drop this one. Then we get approximations to the equation. So let's drop this one. Drop this one. And we get to 1 approximations. And here the approximation, the WI is the approximations to the value to the YTI, and the WI satisfies the following equations. So we have actually on the right side here, WI is WTI plus WI plus 1. And on the right hand side, we got this WI plus 1, and then it equals to YTI, and then we are going to use the WI to approximate it. So this is WI, and this is the item here, and then Y prime TI, and then H, and then what's the Y prime TI? And this is just C. So if you look at the equation, and the Y prime TI is just C equals to TI and YTI, right? And now we are saying that we use the YI, WI to approximate the YTI. So here, actually, we have this in the approximation version, and then we are going to have the first one is the F, Ti, and then Wi and H. And this is because, let me just restate this because it's quite confused here. So we are going to have some things, we want something to approximate these items, because the equations we have here, the y point Ti, and then it equals to FTI. This is the original version of the equation, right? And so now we have, but we also stating that the Wi is the approximations to the YTI. And so on the right hand side, and then we are going to approximate it with the FTI and then Wi. And this is because the Wi is the approximation to the YTI. So that's what we have here. We approximate this YTI with this, and then we replace the YTI with the Wi. So that's why I have this item here. And the next, as you can see, we have the second derivative. This is our, so we treat this as the first derivative of the y towards regarding the the time variables at Ti. And here, this is the second derivative, and which means that after you can get the first derivative of this one. And then so that we get the second derivative of the y, because this is the first derivative of the y. And then let's get the derivative of this one, and then we get the second derivative of the y. And so here we got, and this is h, and then divided by 2, and then df, ti, and then this means that we are going to, so this means that we get the first derivative of the f function, and then we evaluate the f function derivative at the Ti and Wi point. And for the rest of the things, we are doing the same things, and then this is just a second derivative of the f towards the time variable, and then evaluate at the Ti and omega Wi. So that's the things. Actually, this one should be h squared. And this one, let's see, this one it should be d. This is with the h3, but here this is the second derivative, and then Ti and then Wi. And the next things we have, it should be all the ways to the hn and the n factorial, and then d here it should be n minus 1 derivative, dt n minus 1, and then you evaluate at Ti. This is the f function's derivative, and then you evaluate at the Ti and the Wi. And this is the formula we have here, and for the Wi plus 1 updating rules. Actually, we can write this in this format. So let me conclude all the things here. So what we have here is the Taylor's methods of the order n. Taylor method of order n. And as we have before, and then this is the same as the Wheeler's methods. We set the W0 to the initial value, so there's no error in the initials for the W0. And for the Wi plus 1, and then we are using this updating rule. And actually, we can write the formula in this way. So we have the H here, and then this is the Taylor Tn, and then n represent the order we have here. We are having the order n method, and then and it's all about the TI and WI. And as you can see here, the TN, this is the TN, and then the TNWI, TIWI, this function, and then it equals to, so we are just concluding something from here. And so there's a H step size here, and then times the formula, and then formula we have here, it should be FTI, and then WI, and then plus the H divided by 2, and then F, I should write down the DT compared to the textbook one, and then I love to use the D and then divide D and DT notation here, because it's clear that we are going to get the derivative regarding the T variable and TIWI. Plus, oh, I should write this one as H3 divided by 3 factorial. And so here the third item should be H squared, and that's 3 factorial. So here is 2 factorial. D, and then second derivative FTI, and then WI, and then this is, should be the DT2. And then all the way to H n minus 1, and then n factorials, and then D n minus 1. And actually you don't need to write it in this format, and then the previous one, the orange one, is already very good, but they have such a research to write the things in this way. This is the Taylor's methods of the edit order n, and let's say, okay, and then what's the connections between the things you learned last time, between the Euler's method and the Taylor's methods. As you can see in the derivation, the Taylor's method is just expanding doing the expansions to the n order term, and then the Euler's methods, and then we just goes up to the first order term, and the connections is that the Euler's methods is actually a Taylor's methods. So this is Euler's methods is the Taylor's method, but it's with order n, with order 1. And that's the things. This is the connections between the Euler's method, Taylor's methods. And as you can see here, the Euler's methods is the most simple versions we have for the Taylor's method. And that's it. Any questions? So next time, I'm going to show you one examples about this. And once we finish this part, and then we are going back to talk about the sequence method, and before we move to the next part. That's all the things I want to include here. Let us meet next week. And also, if you come up with one method to estimate the M, and then here without knowing the exact solution, then please tell me. I believe there's one way to do it. The bound for the Y. The last one?
Yeah.
Okay.